This video will cover section 8.5, which is talking about integration with partial fractions. Now, partial fractions is something that you probably learned in pre-calculus or maybe even algebra 2. It's just a way that we can decompose a rational function, so as in number 1, 5 over x squared plus x minus 6, into a sum or difference of two fractions. Now, I'm going to review how to do this for examples 1 and 2. And the reason why is because if I were to give you this, like in number 1, to integrate, you could not integrate this because you couldn't take the natural log. And I know that in class earlier we talked about, let's say, taking the integral of something like 1 over 4x plus 13. Now, when I was integrating that one, what I did in class is we completed the square. So then we made that the integral of 1 over, I believe it was x plus 2 squared and then plus 9, I think is what it was when we completed the square. And so then that became an arctangent problem. All right, so the reason why we completed the square there is because when you look at the denominator, x squared plus 4x plus 13, that does not factor. So we had to complete the square so we could make it into a form that we could find the integral of. All right, so what we're doing today is doing partial fractions. So when we have that, what we want the denominator is to be able to factor. So you look at the first one, decomposing this into a sum or difference of two fractions. So the first thing that I'm going to do is factor the denominator, which factors into x plus 3 and x minus 2. And so what we want to say is that's equal to two separate fractions, and we don't know what the numerator would be. So a over x plus 3 plus b over x minus 2. So somehow this fraction decomposes into two different fractions, and I have to figure out what a and b are. And no, you can't just simply split up 5 into 2 and 3 or 4 and 1 or whatever and make those a and b. Now, my next step in decomposing into a sum or difference of fractions is to multiply this whole thing by the numerator. So we're clearing the fraction, essentially. So I'm going to multiply this whole equation by x plus 3 by x minus 2. And so when you do that, you get 5 equals a times the other factor, x minus 2, plus b times the first factor of x plus 3. Okay, so this is where you want to be for a partial fraction. So now to figure out what a and b are, notice you have one equation with 3 unknowns. So somehow you've got to clear out some of those unknowns. So the way we're going to do that is we're going to make clever forms of x in order to clear out those fractions. So think of like the zeros here. So like, what would x be under this a factor to make that whole thing go away? Well, if x equals 2, then that whole factor would go away. So if x were to equal 2, what I'm going to do is I'm going to like plug in 2 everywhere I see an x and see what I get. So I would get 5 equals, now this a term is going to completely cancel out if I plug in 2 for x. So then if I plug in 2 for this x, then you get 2 plus 3 is 5b, and therefore b would equal 1. Okay, so then you would do the same thing for the b in order to solve for the a. So now over here for the b, I'm going to make my x be equal to negative 3. And so if x equals negative 3, then you'll get the equation 5 equals, the b is going to cancel out. And if I plug in negative 3 for x, you would get negative 5a, making a be negative 1. Okay, so now you found a and b. So now all I have to do is plug in a is negative 1 and b is positive 1. And that is how that fraction decomposes. And you can see now, if you look at those two individual pieces, you can integrate each of those pieces, and that's the whole goal here. So what I want you to do is I want you to try to decompose number 2 by yourself. Okay, now here's what I have initially. Now, I want you to see that obviously I put a over x minus 3, but you might have put a over x plus 1. It really doesn't matter for this problem. In the end, you're going to get the same product. So if you go by with what I have, then I'm going to continue on. If you have your factors flipped, then you should get the same answer at the end. So again, pause your video and continue on. Okay, so I found that for my problem, b is equal to 3 and a is equal to negative 2. So hopefully hopefully you got the same factors as I did. And just in case if you're confused, on the left side over here we have this x minus 11, which we did not have in the first problem. So all I did is if x is equal to -1, I just plugged that -1 into x to get that -12 here. And same thing over here, if x is equal to 3, then I plugged in 3 in for x, so 3 minus 11 is -8, and that's where those numbers came from. Okay, so now that we got practice with decomposing partial fractions, we're going to actually integrate this problem. Again, what you're looking for is if the denominator can factor, then we're going to go partial fractions. If it cannot factor, then you would go with completing the square. All right, so let's go ahead. What I want you to do is I'm going to pause again. I want you to decompose this, and then we'll come back to the integral together. So I'm going to completely decompose this and get it into its new format. So do that on your own, pause the video, and then we'll come back. Okay, so here I decomposed my fraction. And I get b is equal to -1/7, a is equal to 1/7 positive. And so when I replace the a and the b, I get what I have down here in black. Okay, so hopefully that's what you got. Now I'm going to talk about the integral here. Now the 1/7 and the -1/7, I can actually take those out of the integral. So I'm going to have 1/7 times the integral of 1 over x minus 6. And then that would be minus 1 over x plus 1 dx. And now these are of the format that I can take the integral. So I have 1/7. The integral of 1 over x minus 6 is natural log of absolute value of x minus 6. And also I'm going to put the 1/7 in front of brackets there. And then minus the natural log of the absolute value of x plus 1. Then, of course, plus c. So this is not simplified, so if you use your natural log rules, this would be 1/7 times the natural log of the absolute value of x minus 6 over x plus 1. And if you got really into it, then you could take that to the 1/7 power, but I'm not going to. All right, so this is what I would say is my final answer. Okay, so now for like a really good problem. So for number 4, we got a lot going on here. Now, I will remind you that, remember, if you have a polynomial divided by a polynomial, a rational function, always check to see if the degree in the numerator is greater than or equal to the degree in the denominator. Then you would do polynomial division. However, for this problem, it is not. So the next thing that I would try to do is look to see if anything factors. If you look at the top actually does not factor, and the bottom you can factor out in x. So I'm going to go ahead and do that first. Okay, so now when you fully factor the denominator, you would get x times x plus 1 times x plus 1. All right, so now what we're going to do is we're going to decompose this. And so this gets a little bit weird with the double x plus 1s, but I'm going to go ahead and set it up. I'm going to set up my decomposition, and then I'll come back. Okay, now since that factor in the denominator was originally a cubic function, what that means is I need to have 3 separate factors here, 3 separate terms that I'm adding or subtracting. So you can see I've set this up to be a plus b plus c over some kind of factor. Now, what a lot of people are tempted to do is say a over x, then b over x plus 1, and then c over x plus 1. But think about this for a second. And don't write this down, just watch for a second. If I were to take this, and a, b, and c are just arbitrary numbers, we could even say 1. All right, let's just say 1. Again, don't write this down, just watch. So if I have 1 over x plus 1 over 1 x plus 1 plus 1 over x plus 1. If you were to add those terms together and bring them together, you would have to find a common denominator. Well, the x plus 1s are already in common. So that means that I need to have an x plus 1 term. So my common factor is x times x plus 1, right? So I would multiply here by x plus 1. I'd multiply this by x over x. And I'd multiply this one by x over x. Okay, so what would happen is if you used what I have in black, x plus 1, and x plus 1, then what your common factor is going to be in the denominator is just x by x plus 1, which is not what we want. What we want is x times x plus 1 times x plus 1. Okay, so hopefully that demonstrated to you that what I had originally in black actually doesn't work. So I'm going to erase that really quickly. Let's see. Okay, so what you actually want to do in order to get that x plus 1 is you have to have 3 distinct fractions, And so each denominator has to be different. So I have x plus 1, and so here's how you make up for that. That x plus 1 is squared, right? So what you can do is you can make that final one squared, and so what you would have is 3 distinct denominators, which is what you want to have, and where the common denominator, if I was to find the common denominator, would be x times x plus 1 times x plus 1, which in this case would be. So just to prove it to you, this x right here would need, if my common denominator I want to be this right here in red, then this x would need an x plus 1 squared, correct? And then this x plus 1 would need an x by x plus 1, and then this guy over here would just need a single x. And then you would have that common denominator of x times x plus 1 times x plus 1. Okay, so hopefully y'all understood that. All right, so let's go back now. I don't know what we're doing here. Hold on, I'm trying to undo. Hold on. Okay, so now that I hopefully made that make sense, now we're going to go back and figure out how to find these a, b, and c. Okay, so the next step on our list would be to multiply through by that common denominator. So over on the left, we have 5x plus 20x plus 6 equals a, and then just like I was showing to find the common denominator, we would have a times x plus 1 squared plus b times x plus 1 plus c times just an x. Okay? All right, so now we need to plug in clever forms of x so that we can figure out what a, b, and c are. Now, so I'm going to start off with the a, and we're going to say x equaling -1, right? That would make that go to 0. And then if you look at b, the b, that will also go to 0 because the -1 here would make that go to 0. So good, that cancels out the a and the b, which is what you want. You just want the c left over. All right, so when I plug in -1, you're going to have to plug in -1 into this whole thing over here. So calculate that. That'd be 5 minus 20 plus 6, I believe. So that would be, what, -9? And then that would equal, if I plug in a -1 over here, that would be a -c. So therefore, c would equal 9. Okay, so the next logical thing that I would say is let x be equal to 0. So if x equals 0, that would knock out the b term, it would knock out the c term, leaving the a term. So if I plugged in 0, over here on the left, I would get 6 equals just a. All right, so now we have a and b. So now for c. So I plugged in -1, I've plugged in 0. So what I need to do is I need to try to cancel out the b term without canceling out the a and the c, and I can't. I don't have anything left over. So what you can do now, because I've exhausted my zeros, right? My zeros are only 0 and -1. So what you need to do now in order to find the b is I know a and c. So just come up with another form of x. It's just easy to evaluate. So the next easiest thing to evaluate besides -1 and 0 would be 1. Now, not everything's going to cancel, but now you have some unknowns of a and c that you can plug in. So if x equals 1, on the left you would get 5 plus 20 plus 6, which is 31. And on the left, you would have this a would be 9 times x is 1, so that would be 2 squared. Okay, I knew I made a mistake, so sorry. That a should have been a 6, not a 9. There we go. Okay, so then plus the b, which is my unknown. So that's going to be b times 1 plus or times 2, so that would be 2b. And then the c we have would be c is 9, x is 1, so that'd be plus 9. Okay, so a lot of algebra going on there. All right, so we have 31 equals, that would be 6 times 4 is 24, plus 9 is 33, plus 2b, and then when we solve that all out for b, you get 2b equals -2, and then b is equal to -1. Okay, so kind of tedious there, but that's how you would have to do that one. Okay, so finally we have our a, b, and c, and now we have to go back and integrate this whole thing. Okay, so now we have the integral of a over x, so that would be 6 over x, plus b over x plus 1, so that would be minus 1 over x plus 1, and plus c over x plus 1 squared, so that'd be plus 9 over x plus 1 squared. Now we've broken this down into a format that we can actually integrate. So the integral of 6 over x is 6 times the natural log of absolute value of x minus the natural log of the absolute value of x plus 1. And don't get in the habit and say that's 9 natural log, because that is not a natural log because the denominator is squared. So that last one you actually have to use regular u substitution with, where u is x plus 1, du is dx. So that would be plus 9 times the integral of 1 over u, 1 over u squared du, which I prefer to write 1 over u squared when I'm integrating as u to the negative 2. All right, so now let's clean this up a little bit more. We can go ahead and use our natural log rules. This would be 6 natural log of the absolute value of x over x plus 1. And again, if you'd like to make that to the 6th power, that's fine as well. Or actually, no, I take that back. That whole thing wouldn't be the 6th power. That would be wrong. Just the x would be the 6th power. Then plus, when I integrate u to the negative 2, you get negative 1 over u. So that would actually be a minus 9 over x plus 1 plus c. Wonderful problem. Sorry that took like 10 minutes, but that is how you do integration with partial fractions.